Alright, so now we're on the third question on Jim Coroneos' list of 100 integrals. And the integral that we have been given to solve is the integral of 5x plus 2 all on the quantity x squared minus 4 integrated with respect to x. So how do we deal with this, right? We notice that the numerator is a degree less than the denominator. And I mean, we could instantly think, oh yeah, that's sort of like, we have the derivative on the bottom, and that's on the top, and we could take natural logs. But what what the obstacle is in this case, is the 2 that's being added in the numerator, and that 2 is really preventing us from doing, solving this to be a simple natural log. So how we tackle this is we split the integrals, just like how we can split a fraction. We can split 5x plus 2 on x squared minus 4 into 5x on x squared minus 4 plus 2 on x squared minus 4, right? That's what we can split the integral into. The fraction into. And by splitting the fraction, we can also split the integral, because if we have the integral of the integral involving the integrand having a sum, then we can split that integral into two separate integrals that are being added together. So what do I mean by that? I mean that this integral is equal to the integral of 5x on x squared minus 4 plus the integral of 2 on x squared minus 4. And each of these integrals is integrated with respect to x, right? And so that's what we get. It's an equivalent statement. And now, right, on this first integral we have, which is 5x on x squared minus 4, we can see that this is almost in the form of the integral of f prime of x on f of x dx, right? Which would give us the natural log of whatever function is on the denominator, right? We can see that it's almost there, but we have a 5 there, right? And really, if we take the derivative of whatever's in the denominator, which is x squared minus 4, we really should be getting 2x, but there's a 5 in the front of the x, a coefficient of 5. So we're going to change that 5 into a 2, but we have to keep this integral the same in some way. So how we do that is, since 5 is a constant, we're going to take the 5 out, and we're going to have x on x squared minus 4 integrated with respect to x, and I might rewrite this integral as well. But in order to get the numerator to be the derivative of the denominator, which if we do take the derivative will be 2x, what we can do is we can multiply the numerator by 2, and then we can divide it by 2, which is equivalent to saying multiplying by a half. Right. So we do indeed have f prime on f now, but since half is a constant, we can take the half out of the integral, and that half is going to multiply with the 5. So we're going to get 5 on 2 multiplied by the integral of 2x on x squared minus 4, and that's going to give us the natural log, right? So solving this integral, we get the natural log of f of x, which in this case is x squared minus 4, right? And to that, we're going to add this integral. Now, 2 is a constant in this integral, so we can take that out the front, and we're going to have dx on x squared minus 4. But as you know, x squared minus 4 is a difference of 2 squares, right? And we can split that into x minus 2 multiplied by x plus 2. That's an equivalent statement. And from here, now we have to do partial fraction decomposition. And as you learn from partial fraction decomposition, we're going to split this one fraction into two separate fractions, each with their own denominators and with their own numerators. So let's do that. There is a quicker way to do partial fraction decomp, but I'll leave that to another video where it's solely going to be partial fractions. Okay, so we're going to say let 1 on x minus 2 times x plus 2, which is what is pretty much the integrand, and that's equivalent to, now I'm going to introduce two fractions that are being added together, which are going to be a on x minus 2 plus b on x plus 2, right? And as you know, when we have denominators with degree 1, the numerator that we introduce into these two separate fractions will be of degree 0, and that's just going to be a constant. Okay. Now what do we do? Now we're going to combine the right hand side into one entire fraction to make it identical to the, equivalent to the left hand side. And so we're going to combine the denominators, and likewise the first fraction, right, never had an x plus 2 in the denominator, so we have to multiply a with x plus 2. We're going to add that to b, and b never had x minus 2 on the denominator, so we have to multiply it by x minus 2. And that's going to be equal to this left hand side. And now we're going to and we notice that the denominators are the same, but the numerators aren't. So we're going to equate the numerators, because we are assuming that these fractions are equivalent. Equate numerators. And actually, I might move this to the side, because I want to leave some space for solving the integral. And that will be 1 is equivalent to a x plus 2 plus b times x minus 2. Now, I want to find what the value of a is, right? And also what the value of b is after that, right? And what we can do is we can substitute values of x that will get rid of a, and that will get rid of b. And what we're looking for is for a or b to be multiplied by 0. That gets rid of any number, really, if we multiply by 0. So I want to find what a is first. So we're going to get rid of b. And so we want b to be multiplied by 0. And b is currently being multiplied by x minus 2. And we want to turn that x minus 2 into a 0. So we're going to substitute x equals to 2. So let x equals 2. And what we get is 1 is equal or equivalent to a times 2 plus 2, which is 4. And that's being added to b, multiplied by, in this case, 2 minus 2, which is 0. And because b is multiplied by 0, that gets cancelled. So we have 1 is equal to 4a, and let's divide both sides by 4, and hence we get a is equal to 1 on 4, 1 quarter. And now I want b, so we've got to get rid of a. A is being multiplied by the quantity x plus 2, and we want x plus 2 to be equal to 0, and in that case, we're going to let x equal to negative 2. And what we get is 1 is equal or equivalent to a multiplied by 2 minus 2, which is 0, plus b multiplied by, in this case, negative 2 minus 2, which is going to be minus 4. A times 0 gets cancelled, and we get b times minus 4 equals to 1. And making b the subject, we get that b is equivalent or equal to negative a quarter. Okay, so those are two values. I might put that in red. So a is a quarter, b is negative a quarter. And from there, we can pretty much say that, going back to here, we can say that since a is a quarter and b is negative a quarter, therefore we can say that 1 on x minus 2 times x plus 2 is equivalent to, and we've initially introduced the left hand side to be equal to two separate fractions, and a on x minus 2 will turn into a quarter on x minus 2, and that's being added on to b, which is b on x plus 2, and we know that b is negative a quarter, so we're just going to substitute b into there, and that's going to be negative a quarter on x plus 2. But because we have a plus and a minus, right, we have a positive and negative being multiplied, so we can just change that into a negative, right? And 1 on x minus 2 and x plus 2 is pretty much the integrand in this integral here. So we can replace that integrand with whatever's here on the right hand side, right? So let's do that. So therefore, right, our initial integral, right, is equal to, let's call the initial integral I, so it's just easier to write. Let's call this integral I. So therefore, our integral I is equal to, so that would be the natural log of, I believe it was x squared minus 4. Was there a 5 on there? No, it was 5 on 2. So that natural log is multiplied by 5 on 2. And that's going to be added to the 2 times the integral of, in this case, the combined quantity a quarter on x minus 2 minus a quarter on x plus 2. And this quantity is being integrated with respect to x, right? So now, just like before, we can split this integral into two separate integrals that are being subtracted from each other. Okay, because the integrands are the integrand is a difference, and we can split the integrand that's also a difference into two separate integrals that are the difference of each other. So that'll become 5 on 2 times the natural log of x squared minus 4, and that's added to, and we're going to carry the 2 over to these two separate integrals, so that's going to be 2 times the integral of quarter on x minus 2 dx minus 2 times the integral of a quarter on x plus 2 dx, right? And now, let me just carry on this last line here. I'm sorry, this x squared minus 4 log. A quarter is a constant, so we can take a quarter out. And since a quarter is going to be multiplied by 2, we're going to get a half outside. So that's going to be half times the integral of dx on x minus 2. And likewise, the same thing here. A quarter is a constant. We can take that out. That's being multiplied by 2. We're going to get a half. And that's going to be half times the integral of dx on x plus 2. And here we can see that these two integrals are in the form of the integral of f prime of x on f of x dx. And that's going to give us the natural log, ln, of f of x. Right? And so, that's what we'll do. And we're going to finish off our answer soon. Two more lines. That's going to give us 5 on 2 multiplied by the natural log of x squared minus 4 plus, I might factor the half out actually. Now the first integral will be dx on x minus 2. Remember, I factored the half out, okay? And that's going to turn into the natural log of x minus 2. And from that, we're going to subtract the integral of dx on x plus 2, which is the natural log of x plus 2. Right? And so we can combine those logs using logarithm rules. When we have two logs that are subtracted from each other, whatever's inside the parentheses will be divided. So it will be the natural log of x minus 2 on x plus 2. Right? And of course, that's going to be added. We're going to add the constant of integration at the end. And that's pretty much the end of the question. And I mean, there's a lot of work. I mean, we've had a simple natural log integral, a simple integral at the beginning that could be converted to a natural log, and then we had to do partial fraction decom, which is pretty tedious, but we got there in there. So that's the end of the question.